All right, welcome to category theory lectures. And so, are we all programmers here? Or is everybody a programmer? Or are there people who are not programmers? If you're not a programmer, please raise your hand. Okay, means like you don't really write any programs?
Try to learn as a hobby.
Ah, okay, okay. Well, that's good enough. Okay, and how many people here have a little bit of knowledge of Haskell? Oh, okay. Oh, lots. That's excellent, because I might be giving some examples, mostly just like, you know, declarations of functions or something like that. I'll explain everything, but it's good to have a little bit of understanding. So I'm not really teaching a programming language here. It will be about category theory, and category theory is like this most abstract, well, or maybe almost the most abstract part of mathematics, right? So the question is, why are we here? What does it have to do with programming, right? And a lot of programmers, they hate math, and it's like they finished learning math at college, and now they are really happy. Now for the rest of my life I will not have to touch it. I hate math and so on. And you guys here come for, I don't know, punishment. Why do you think category theory might be important? What do you think? I mean, do you do functional programming? Is category theory only relevant to functional programming, or other branches of programming would maybe profit from it too? Is that something more general? Have you heard of functors? Who heard of functors? Yeah? And who knows what functors are? Aha, fewer. That's good. Oh, that means I can actually explain some stuff, and it won't be totally like repeating what you already know. So I came to category theory through a long, long, twisted road. Okay, when I started programming, I started programming in assembly language, like the lowest possible level, right, where you actually tell the computer exactly what to do, right, down to grab this thing from memory, put it in the register, use it as an address, and then jump, and so on. So this is very precisely telling the computer what to do, right? This is a very imperative way of programming. We start with this most imperative approach to programming, and that sort of we drag this approach to programming throughout our lives, right? And like we have to unlearn at some point. And this approach to programming, sort of in computer science, is related to Turing machines. A Turing machine is this kind of very primitive machine that just stamps stuff on a paper tape, right? There's no high-level programming there. It's just like, this is the assembly language. Read this number, put it back on tape, erase something from the tape, and so on. So this is this one approach towards programming. By the way, all these approaches to programming were invented before there were even computers, right? And then there's the other approach to programming that came from mathematics, the lambda calculus, right? Alonzo Church and these guys. That was like, what is possible to compute, right? Thinking about mathematics in terms of how things can be actually executed in some way, transforming things, right? So these approaches to programming are not very practical. Although people write programs in assembly language, and it's possible, but they don't really scale, right? So this is why we came up with languages that offer higher levels of abstraction, right? And so the next level of abstraction was procedural programming. And what's characteristic of procedural programming is that you divide a big problem into procedures, and each procedure kind of has its name, has a certain number of arguments, maybe it returns a value sometimes, right? Not necessarily, maybe it's just for side effect and so on. But because you chop up your work into smaller pieces, and you can like deal with bigger problems, right? So this kind of abstracting of things really helped in programming, right? And then next, people came up with this idea of object-oriented programming, right? And that's even more abstract, because now you have stuff that you are hiding inside objects, and then you can compose these objects, right? And once you program an object, you don't have to look inside the object. You can forget about the implementation, right? And just look at the surface of the object, which is the interface. And then you can combine these objects without looking inside, and you have the bigger picture, and then you combine them into bigger objects, and so you can see that there is a certain idea there, right? It's a very important idea that if you want to deal with more complex problems, you have to be able to chop the bigger problem into smaller problems, right? Solve them separately, and then combine the solutions together, right? And that there is a name for this. This is called composability, right? So composability is something that really helps us in programming. What else helps us in programming? Abstraction. Abstraction, that comes from a Greek word that means more or less the same as subtraction, right? Which means getting rid of details. Like you want to hide details. You don't want to, you want to say, these things, they differ in some small details, but for me they are the same. I don't care about the details. So an object in object-oriented programming is something that hides the details, abstracts over some details, right? And there are even these abstract data types that just expose the interface, and you are not supposed to know how they are implemented, right? So, so when I first learned object-oriented programming, I thought this is like the best thing since sliced bread, and I was a big proponent of object-oriented programming, and together with this idea of abstracting things and composing things comes the idea of reusability, right? So if I have these blocks that I have chopped up and implemented, right, maybe I can rearrange them in different ways. So once I implemented something, maybe I will use it in another problem to solve another problem. I will have these building blocks, I will have lots of building blocks that hide their complexity, and I will just like juggle them and put them in new constellations, right? So it seemed to me like this is really the promise of object-oriented programming. I'm buying it. And I started programming in an object-oriented way using C++, and I became pretty good at C++. I think, I wrote a lot of C++ code. Well, it turns out that there is something wrong with this object-oriented approach, and it became more and more painfully obvious when people started writing concurrent code and parallel code. Okay, so concurrency does not mix very well with object-oriented programming. Why doesn't it? Because objects hide implementation, and they hide exactly the wrong thing, which makes them not composable. Okay? They hide two things that are very important. They hide mutation. They mutate some state inside, right? And we don't know about it. They hide it. They don't say, I'm mutating something. And sharing. They use pointers, right? They share data. And they often share data between each other, you know, between themselves. They share data. And mixing sharing and mutation has a name. It's called data race. Okay? So what the objects in object-oriented programming are abstracting over is data races. And you are not supposed to abstract over data races, because then when you start combining these objects, you get data races for free. Right? And it turns out that for some reason we don't like data races. Okay? The same thing is with, you know, so once you realize that, you think, okay, now I know how to avoid data races, right? I'm going to use locks. And I'm going to hide locks too, because I want to abstract over it. So like in Java, like every object has its own lock, right? And unfortunately, locks don't compose either, right? That's the problem with locks. I'm not going to talk about this too much, because this is like that was a different course about concurrent programming. But I'm just mentioning it that this kind of raising the levels of abstraction, you have to be careful what you're abstracting over. What are the things that you are subtracting, throwing away, and not exposing, right? So the next level of abstraction that came after that, well, it actually came before that, but people realized that, hey, maybe we have to like dig it out and start using. That's functional programming, when you abstract things into functions, okay? And functions, and especially if you in Haskell, when you know, in a functional language you don't have mutation, so you don't have this problem with hiding data races. And then you also have ways of composing data structures into bigger data structures, and that's also because everything is immutable, so you can safely compose and decompose things, right? And now every time I learned a new language, I wanted like to find where the boundaries of this language are. What are the hardest thing to do in this language, right? So for instance, in C++, right? What are the highest levels of abstractions that you can get? Template metaprogramming, right? I was really fascinated by template metaprogramming. And I started reading these books about template metaprogramming, and it's like, wow, this is like I would never come up with these ideas. They are so complex, right? So what it turns out that these are very simple ideas. It's just that the language is so awkward in expressing them. So I learned a little bit of Haskell, and I saw, okay, so this huge template that was so complicated, that's a one line of code in Haskell, right? Okay, so there are languages in which like jump the level of abstraction and make it much easier to program at a higher level of abstraction, right? And in every language, you know, there is this group of people who are writing libraries, right? And they always stretch the language. They always go to the highest possible abstraction level, and they hack, right? They hack at it as much as possible. So I thought, okay, I don't like hacking. I just want to use a language that allows me to express myself at a high level of abstraction, and that lets me express new ideas that are much more interesting. You know, like with template metaprogramming, right? You express this idea that you might have lots of data structures that only differ by the type that they hide, right? Like you can have vector of integers and vector of booleans, right? And there's just so much code to share. So if you abstract over the data type that you are storing there, like if you forget about it, hide it, abstract over it, you can write code, and abstract code, and in C++ you do this with templates, right? And you get something new. You program at a higher level, right? A higher abstraction level, because you disregard some of the details. So that was great. Now it turns out that so once I learned Haskell, I'm still learning Haskell, but you know, to some extent, then I found out, okay, there are things in Haskell that are at these boundaries of abstraction. That's like, there are people who are working on this frontier of Haskell, right? There are certain very abstract things that are, unfortunately, they are a little bit awkward to express in Haskell, right? And then there is this barrier to abstraction even in Haskell, right? And I mean, if you've seen some libraries that were written by Edward Kmet, you realize, you know, that they are really extremely hard to understand. It's really hard to understand what was the thought process, right? And the secret is very simple. Category theory, okay? Edward Kmet knows category theory. And he just takes the stuff from category theory, he reads these mathematical papers, and he just translates them into Haskell. And when you translate stuff from category theory to Haskell, you lose a lot of abstraction. You make it more concrete, right? You sort of, Haskell has one category built in, and you are restricting yourself to this particular category. And I mean, you can create other categories in Haskell. You can model them, right? But that becomes awkward. That becomes sort of like template metaprogramming, you know, within Haskell. Not exactly the same mechanism, but the level of difficulty in expressing these ideas in Haskell is as big as template metaprogramming in C++. So, the category theory is this higher level language above Haskell, above functional programming, above ML, Haskell, Scala, and so on, C++, assembly. It's a higher level language. Okay, it's not a practical language that we can, like, you know, write code in, but it's a language. So just like, you know, people who write these horrible metaprogramming template libraries in C++, they can only do this because they learned a little bit of Haskell. Right, and they know what you know, what some constructs in Haskell are, and how to do things that are, you know, how to implement algorithms on immutable data structures. right? They know how to do this because they learned it from Haskell. And they just translate it into this horrible template programming language. Fine, right? And it works, and people are using it. The same way, if you're a functional programmer, you know, you can take these ideas from category theory, these very, very abstract ideas, and translate it into, well, this kind of awkward language called Haskell, right? Now, looking from categorical perspective, Haskell becomes this ugly language, just like looking from Haskell, C++ becomes this ugly language, right? But at least, you know, it's an executable language. It's a language in which we can write programs. And of course, these ideas, when they percolate from category theory down to Haskell, they can also percolate then down to C++ and maybe even to assembly or PHP or whatever, you know, JavaScript, if you want to, because these are very general ideas. So we want to get to this highest possible level of abstraction to help us express ideas that later can be translated into programs. So that's, for me, is the main practical motivation. Okay? But then I started also thinking about like theoretical motivation or more philosophical motivation. Because once you start learning category theory, you see, okay, category theory unifies lots of things. I mean, if you abstract enough, right? If you chop up all the unnecessary stuff, and you are, you know, on top of Mount Everest, and you are looking down, then suddenly all these things start looking similar. Okay. Like from that high level, you know, all these little programming languages look like, you know, little ants, and they behave the same way, and it's like, okay, they're all the same. At that level of abstraction, all this programming stuff, it's all the same. It looks the same. But that's not all. Suddenly at this high level, other things look the same. Okay? And then mathematicians discovered this. They've been developing separate areas of mathematics, right? So first of all, they developed geometry, algebra, number theory, topology, what have you, right? Set theory. These are all completely different, separate theories. They look nothing like each other, right? And category theory found out similarities between all these things. So it turns out that at a certain level of abstraction, the structure of all these theories is the same, right? So you can describe, you tweak with the structure of a category, and you suddenly get topology. You tweak the structure of category, right? And you suddenly get set theory. You tweak something else, and you get algebra. Okay, so there is this unification, this grand unification of essentially all areas of mathematics in category theory, right? But then there is also programming, right? Programming that deals with these computers, with these memory and processor registers, okay? And this stuff can be described also, and there are programming languages. This stuff can be described mathematically as lambda calculus, like all these languages that they essentially have roots in lambda calculus. They try to get away from bits and bytes and go-tos and jumps, right, and loops, and they want to abstract this stuff into stuff that's more like lambda calculus, right? And there are these data structures, and these data structures, we used to look at them like, here's a bunch of bytes, here's a bunch of bytes, here's a pointer from this bunch of bytes to this bunch of bytes, and so on, right? Like very, very low level, like the plumbers working with tubes, right? And then computer scientists say, well, actually these things, they form types. Okay, so there's type theory. There's type theory that can describe all these categories of data structures, right? And but there is also type theory in mathematics, right? People invented types in math not to solve problems that computer scientists have. They try to solve problems like paradoxes, like there is Russell's paradox, okay, that says if you want to, you cannot construct a set of all sets, okay, things like this. Or maybe you know this barber's paradox, where the barber can shave himself or not. You know, every barber shaves only people who don't shave themselves. So can he shave himself or not, right? This kind of paradox, I mean, these are funny paradoxes, right? But they are serious. So this barber's paradox actually can be translated into Russell's paradox, which is like the set of all sets, or can a set contain a set that, you know, like sets that don't contain themselves, don't form a set, and so on. Stuff like this, right? And Russell came up with this theory of types that to like say that sets form layers upon layers, that you cannot just, you know, have all sets and put them in one big set, right? And then the type theory evolved from this, and there's this very abstract Martin Love type theory, very formal, right? So that's just a branch of mathematics that was created to deal with paradoxes. And then there is logic, and logic was created, you know, long time ago by the ancient Greeks, right? They used logic. So there are laws of logic, and people have been studying logics for thousands of years, right? And at some point, people suddenly realized that all these distinct areas of mathematics are exactly the same. This is called the Curry-Howard-Lambeck isomorphism, which says that whatever you do in logic, right, can be directly translated into whatever you do in type theory. That they have actually exactly, it's not like they are similar, they are exactly the same. There is one-to-one correspondence, right? And the Lambeck part of this isomorphism says that category theory, there are certain types of categories, you know, the Cartesian complete categories that they are actually totally describe the same thing. So it's like there are these three different theories. One is about computing, right? One is about categories, another is about types, and they are all the same. So like essentially all our human activity is described by one theory. Okay? So this is like really mind-blowing. And of course, mathematicians, you know, when they discover things like this, they turn philosophical, or I wouldn't say religious, but at least philosophical, right? It's like, oh my God, we are discovering stuff. It's like you're not really creating mathematics, right? You're discovering some deep, deep truth about the universe, okay? Like, what do you think, Amy? Is mathematics something that we invent, Or is it like built into the universe? Because physicists know, right? Physicists do experiments. So like we study stuff that, you know, we throw these atoms at each other, bang, bang, right? And we observe something. So we are discovering stuff that's around us, right? Whereas mathematicians, no, they just sit down at the desk, right? With a pencil or walk around in a park and think, right? What are they discovering? And now they are saying, well, we have independently discovered this branch of mathematics. This guy discovered this branch. This other guy in ancient Greece, he discovered logic, right? This guy in Sweden discovered type theory, you know? And they discovered the same thing. There is some really, really deep truth in it that we are discovering. So it's like there is some Platonic idea, right? I don't know if you've read the Stevenson's novels about like there's this novel in which there are multiple universes and each of them is more Platonic than the other. And just like people move from one Platonic universe to another. But mathematicians think that this is really what they are doing, right? So, and I was thinking about it, and I thought, no, this is really not. There has to be a simpler explanation, okay? And that goes back to the way we do mathematics, or we discover the universe, right? So, what do we do? I mean, we are like human. We humans, right? We are these evolved monkeys, right? Now we have evolved our brains. So some parts of our brain evolved, you know, since I don't know, 1 billion years of evolution, right? The image processing stuff, for instance, has been evolving for a very, very long time, right? So this is really, really very good system that to like analyze visual input, right? That's been evolving for a very, very long time, starting with bacteria that would just, you know, see whether it's bright or dark and change their metabolism, or you know, then they would start seeing, oh, this side is brighter than that side, and so on. And then eventually, you know, like the most important thing, where's the predator, right? Where's the food? Like distinguishing between the predator and the food, right? This is like the most important thing that makes you survive, right? And so we got very good at this. And we have inherited this stuff from lower animals. And there's been a lot of evolutionary pressure to evolve these things, right? And now we are trying to imitate this stuff with computers, and we are finding it's really, really hard. It's a really hard problem, image recognition, right? And recognizing who's your foe and who's your friend, and recognizing where the food is, right? And then whether it's spoiled or not. Very important things. Computers don't do it very well, okay? So this is a very hard problem, but we've been working on it for 1 billion years, right? So our brains know how to do this stuff. But then there are things that evolved in the last 100,000 years or so, right? Or I don't know, how long is human evolution? 100 million years? No, that's not. Whatever it is, it's a tiny number, right? It's just like the last millisecond of evolution. That we suddenly had these brains that can actually think abstractly, right? We can count, we can communicate, right? We can organize stuff, right? and we can do math, and we can do science. And this is like a really, really fresh ability, right? And we've been doing science for the last few thousand years only. So that's nothing on the evolutionary scale. And we are doing with these brains. Where do these brains come from, right? They evolved to do things like hunt mammoths, okay, or run away from saber-toothed tigers, okay? They did not evolve to do programming. That's a very, very recent thing, right? They didn't evolve even to do mathematics or logic. No, they evolved to do stuff like hunting, like finding food, and especially organizing ourselves into groups, right? Social activities, right? So and communicating. So language, right? So we have these language skills. This is a very fresh thing, right? So compared to the complexity of our visual cortex, this newly acquired ability to actually think abstractly and using a language, that's a really very, very fresh thing. And it's very primitive, okay? It hasn't had time to evolve. It's very simple, and we are using this tool that we evolved to throwing, javelins or arrows, shooting arrows and communicating with other guys like, oh, here, the mammoth is over there. No, don't run there, or right behind you, a saber-toothed tiger, right? Or a bear. So we are now using this tool to do mathematics. So there are certain things that we found useful in doing abstract thinking, okay, in doing mathematics. And the major thing is we come head to head with a very complex problem, like how to provide food for our tribe, right? And we solve it. How do we solve it? We divide it into smaller problems that we can solve. And then we combine the solutions, okay? So this is the only way we know how to deal with complex situations, by decomposing these things into simpler things, and then solving them, the simplest problems, and combining the solutions into bigger solutions. And this is everywhere, okay? You find this is so permeates everything we do that we don't even notice it, okay? But this is how we work. And because this is how we work, this is how we do science as well. So every branch of science, every branch of mathematics we can only see these things that can be chopped into pieces and then put together. So no wonder they look the same, okay? Because we can only see these problems that have the structure. If they don't have the structure, we just don't see them. We just say we cannot solve this problem, okay? Let's do something else. Maybe we can get grant for solving that other problem because that seems choppable into smaller pieces. This one doesn't. Let's forget about it. Let's not even talk about it, right? So one could think, okay, so maybe the whole universe is like this. Maybe everything in this universe can be chopped into little pieces and then put together, right? Maybe that's like the property of this universe, and our brains are just reflecting this, okay? And personally, I don't think so. Maybe I'm wrong, and hopefully I'm wrong, but I'm a physicist also. I mean, I started as a physicist, right? So I saw what was happening in physics. And in physics, we also wanted to chop things into little pieces, right? And we were very successful at this, you know, we found out that matter is built from atoms, right? So atoms are these things that we can separate and we can study, right, their properties, and then we say, okay, the property of a rock or a piece of metal comes by combining the properties of these atoms. So we can decompose a piece of rock into atoms, study them, and then recompose it, right? And then we have the understanding of how this is. But then we didn't stop at that, because we wanted to see what's inside the atom, right? So there are these elementary particles, there are these electrons, protons, and so on. So at some level, I mean, if we want to be decomposing things into simpler things, these simpler things have to have simpler properties. For instance, what's the simplest thing that we can imagine for an elementary particle? It has to be a point, right? It should be a point. I mean, if it's a ball, right, then maybe we can cut it, chop it into smaller pieces, and then do the decomposition, recomposition, and so on. So at some level, some lowest possible level, we cannot chop it anymore, and we should find a point, right? So an elementary particle should be a point. That would be like the end of this level of decomposition, right? And we tried doing this, right? And then we have like the standard model of particles in which we assume that particles are points. We sort of cheat, because it turns out that we cannot really deal theoretically with point particles, because they lead to infinities, like 2-point particles when they get very, very, very close together, right? The interaction goes to infinity and everything blows up. So we came up with this renormalization theory, which is like a big hack, you know, to get rid of infinities and so on. And of course, physicists were not very happy with that. So they thought, okay, so maybe at this lowest level, things are not as choppable as we thought. Maybe nature really does not follow this kind of, you know, divide and then combine. So they came up with this idea that maybe elementary particles are strings, right? Have you heard of string theory? Right? Like, what a crazy theory this is. That this most elementary thing is not a point, but it actually is a string, and you cannot chop it, right? It's like the elementary thing is not divisible, but it's not a point. And quantum theory now says, this is another non-choppable piece of knowledge that we found out. It says, okay, so if you have, you know, a bigger system, right? Maybe you can separate it into elementary particles, and you can say, okay, I have a system of 10 particles. I know properties of these 10 particles, right? And I call this system something bigger, like an object, right? And I can find out the structure of this object by looking at these particles. And it turns out in quantum mechanics that a state that they don't add up, okay? A state that has 2 particles is not a sum or a product or a convolution of states of single particle. It's a new state, which follows a different, you know, differential equation. and so on. So we try to separate particles, and suddenly we cut the particles apart, and it turns out that, something weird happens in between when you are cutting, right? You are actually changing the system by separating things, okay? So maybe at the very bottom, or maybe there is no bottom, or maybe at the very bottom things are not separable. Maybe things are not composable. Maybe this composability that we love so much, that is not a property of nature. That's what I'm saying. Maybe it's not a property of nature. Maybe this is just the property of our brains. Maybe our brains are such that we have to see structure everywhere, and if we can't find the structure, we just give up. So in this way, category theory is not really about mathematics or physics. Category theory is about our minds, how our brains work. So it's more of epistemology than ontology. Epistemology is how we can reason about stuff, how we can learn about stuff. Ontology is about what things are, right? Maybe we cannot learn what things are, but we can learn about how we can study them. And that's what category theory tells us. Okay? Let's take a break.